Let's talk about the black-body radiation spectrum. This was one of the most important things. Well, a lot of important things came out of the 19th century, but this was a very, very, very important thing that came out of the 19th century. So here's the idea. When things are in thermal contact, what that means is that they're bumping into each other, having collisions, and sharing energy. So if I've got a hot liquid and a cold liquid, and I pour them together, then the hot liquid is going to give some of its energy to the cold liquid. So the cold liquid will get hotter and the hot liquid will get colder until they're at the same temperature. And that's what thermal contact does. Now, when they get into the same temperature, that's thermal equilibrium. The easy way to think about thermal equilibrium is everybody gets his share. All right, so when you're in thermal equilibrium, all the atoms get the same amount of energy provided that they're using it. There's all these little rules that I don't want to talk about right now, but you can think about it that way. So what about light? I mean, if I'm talking about atoms and they're interacting with each other, atoms consist of electrons and nuclei, and those things are charged. So they ought to interact with the electromagnetic field, so that means that they ought to be able to give some energy to electromagnetic waves. So doesn't light get to play? Yes, light gets to play. And that's a major, major thing, because what that means is that everything that has a finite temperature, everything, in order to be in thermal equilibrium, it's got to give some of its energy to light. And of course, what does light do when you give it energy? It leaves. It's not just going to sit around. It's not, attracted to the matter. It doesn't care. It's just going off. It's like a light bulb. You turn it on and the light leaves, right? So here's the idea. Every object that has a finite temperature is always radiating energy. And this energy just comes from the thermal equilibrium. It comes from the temperature itself. So it's just radiating. I'm radiating energy right now, light energy. So when we go ahead and measure the intensity of the light that's coming off versus the wavelength, we get these real interesting curves. The red curve is for a hot object. The blue curve is for a cooler object. Notice that the red curve has a lot more energy, a lot more intensity. So that means that hotter objects give off a lot more light than cooler objects do. All right? Similarly, we find that there's a little peak here. Notice that the cooler object peaks at a higher wavelength than the hotter object does. So what that means is that as an object gets hotter, it not only radiates more just overall, it also starts to radiate at lower wavelengths. So here, this one wasn't radiating very much at that wavelength before, but then we heat it up, and now that becomes the maximum radiation. All right, so that's the way that blackbody radiation works. These curves are extremely important. They actually led Planck to propose photons. That's where photons come from. They come from this blackbody radiation spectrum. Now, you can also understand this just kind of qualitatively if you've ever seen an electric range. You turn it on, turn it up to high, and what happens? How do you know it's hot? Well, the filament is glowing, right? It starts glowing red. So that's an indication that it's hot. That means that the wavelength of peak emission has moved over far enough that you can actually see visible light. See, at my temperature right now, I'm still radiating, but I'm not radiating in the visible spectrum. You got to be pretty hot to radiate in the visible spectrum. All right, let's get quantitative on this. There's two major formulas that are associated with the blackbody radiation formula. Now, I'm not going to write up Planck's formula because it's kind of complicated, but these are two things that are derived from it. First one is the Stefan-Boltzmann law, and that tells you how much energy per unit time, or how much power is emitted by something that has temperature T. So it tells us that power is equal to sigma. Sigma is the Stefan-Boltzmann law constant. And you can measure it, or you can calculate it from fundamental constants. It's 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. All right. Now that unit, of course, you can get just by saying the power has to be watts. And look what I'm multiplying by. This is the area, the surface area of the object. Obviously, if it's bigger, it's going to radiate more. I mean, think about the Earth. right? The Earth is radiating through every little piece of its surface area. So it's a lot bigger than a beach ball. So I would expect it to radiate a lot more energy. So that's why the area is there. Then we have this E. This is called the emissivity. And you can basically think about it in terms of like greenhouse gases, right? The Earth emits energy, but then some of it's bounced back. So that would make the amount that it's actually emitting less. Okay, so this is the emissivity. All right, it's between 0 and 1. All right, and then we have the temperature. And what's weird about this is that the temperature is to the 4th power. Most of the time we just see things squared, at best cubed. But this is temperature to the 4th power. And it's also the Kelvin temperature. It is not degrees Celsius. It's not degrees Fahrenheit, certainly. It's Kelvin temperature. Now, as you remember from chemistry, Kelvin temperature is Celsius temperature plus 273. Now, what's interesting about that is that room temperature is about 300 Kelvin. So when you look at this number and you say, oh, it's 10 to the minus 8, that's not very much power at all. Think about the fact that you're then going to multiply it by 300 to the 4th power.
With Brightstorm, I never get bored learning because all the teachers have really creative ways of teaching.
As a Brightstorm member, I never felt alone when I studied. I knew that if I needed help with my homework or studying for my next big test, I could always log on to Brightstorm and find a video with a teacher who would explain it to me. I never thought I could get such good grades in school, but with Brightstorm, it's easy.
Seriously, I don't know how I survived in school before Brightstorm.
Only into the right, and I do this until I have 5 centimeters of oil in the right hand side. That's the left hand side. We should change.
Yeah. Doesn't matter where, no.
Conservation of matter or energy or mass or any of those.
So what we're going to do next is look at a couple example problems.
So now what you'll want to do is actually go.
As long as you remember that the height is going to,
Is 5 going to 60? Darn, I ran out of space. Can we do this whole thing again?
you're being asked to find tangent. How do you know which one's A?